The purpose of this experiment was to develop a deeper understanding of a percent error and percent differences by applying them to a real physical system involving acceleration. In our previous experiment, Lab 3, we calculated theoretical and experimental acceleration using a glide and hanging mass system. In this lab, we modified the system by changing one of the masses in order to increase or decrease the theoretical acceleration. Acceleration in a mass pulley system depends on the ratio between the hanging mass and the total mass of the system. The theoretical acceleration is given by theoretical equals hanging mass times gravity over hanging mass plus glide mass. By adjusting either the hanging mass or the glide mass, we can directly affect the acceleration of the system. However, due to real-world factors such as friction, pulley resistance, and sensor limitations, the experimental acceleration may differ from the theoretical value. Percent error helps determine how accurate our experimental value is compared to the theoretical prediction. Percent difference allows us to compare two values, such as old and new accelerations, to determine how much they differ relative to a reference value. Before conducting the experiment, we discussed what it means for a percent difference to be larger or smaller. A small percent difference suggests minimal change between values, while a large percent difference indicates a significant change in acceleration. This discussion helped us form expectations about our results before collecting data. Materials used: an air track system, glide cart, hanging mass set, string and pulley system, motion sensor, computer with graphing software, mass balance, and data collection software. As a group, we decided to decrease acceleration from Lab 3. We chose to change the hanging mass since decreasing the hanging mass would reduce the net force acting on the system and therefore decrease the acceleration. Then, we did not select a tentative theoretical acceleration value beforehand. Instead, we selected a new available hanging mass from the discrete mass set provided in the lab. Since our teaching assistant indicated that solving for mass algebraically was not necessary, we directly substituted the new hanging mass value into the theoretical acceleration formula, which is theoretical equals hanging mass times gravity over hanging mass plus glider mass. Then, using the updated hanging mass and keeping the glide mass constant, we calculated the new theoretical acceleration. We then calculated the percent difference between the old and new theoretical accelerations to confirm that the decrease in mass resulted in a measurable decrease in acceleration. After completing the calculations, we set up the equipment with the new hanging mass. We ensured that the string was properly aligned with the pulley, the glide moved freely along the track, the motion sensor had a clear view of the glide, and the track was leveled. Then we ran multiple trials to obtain the smoothest and most consistent position versus time graph. Last but not least, from the graph, we selected one appropriate method to calculate the experimental acceleration and recorded the value for analysis. For our data analysis, we decided to annotate our old values, which we got from Lab 3, by inputting our acceleration, which is a theoretical value gotten from the last lab, which is 0.568. Then our pass at hanging mass was of 12 grams, and the glider mass was 195 grams. Then we decided to calculate the new hanging mass, which now we decided to use a pound of 2 pounds plus the 7 grams, which is the actual weight of the platform used, which gives us 9 grams. Then we annotated as 9 grams, and the glider mass stayed the same, which is 195. Now to calculate the new acceleration, we decided to use the formula of A equals changing V over changing T, which is the same as final minus initial velocity over final minus initial time, which is equal to the points obtained from our graph, which our final is negative 0.26 minus our initial point, which is 0.27, over our final time, which was 17 minus our initial time, which is 15.5. And after we plug in all of those values into a calculator, we obtain an acceleration of 0.353 meters per second squared. And we go ahead and annotate it into our chart, into our new acceleration. Then we decided to calculate our new theoretical value with the new hanging mass that we obtained with the formula of A equals mw times g over mw plus mc. And then we plug in our values, which for mw was 7 grams, times gravity, which is 9.8, over our mass of the weight again, which is 7 grams, plus mass of the cart, which is 195, which then, if it's plugged into our calculator, it gives us a value of 0.339, and that's our new theoretical acceleration. Now, to calculate our percent difference, we use the formula of percent difference equals old minus new over our old times 100. Which then we plug in our values, which our old theoretical value was 0.56H, and we plugged it in, minus our new one, which is said to be 0.339, over our old, which is 568 times 100, which then, if put in the calculator, it gives a percentage of 33.9% difference. Now, to calculate our percent error, we started by annotating our theoretical that we got from our last equation, and the formula that we're supposed to use is percent error equals theoretical minus experimental over theoretical times 100, which then we plug in our values, which is 0.339 minus our experimental, which was said to be in the first chart, 0.353, over 0.339 again times 100. Now, when we plug in those values into our calculator, it gives us a percentage of 4.1% error. And we go ahead and plug in that value into our chart. Now, to proceed with our last calculation, we annotated in our chart the old experimental acceleration, which was the 0.525, and this value was gotten from the last lap in our velocity chart. It's as per our old experimental acceleration, which is 0.525, which our value was derived from the from our last lab, from the time velocity versus time graph. Then for our new experimental acceleration, it's the one that we calculated previously, which is 0.353. Now, to calculate our percent difference, we use the same formula as previously stated, which is percent difference equals old minus new over old times 100. Then we plug in our values, which is 0.525 minus 0.353 over 0.525 times 100, which then, if it's plugged into our calculator, it gives us a percent difference of 32%. This experiment successfully demonstrated how modifying system mass affects acceleration and how the percent error and percent differences can be used to evaluate accuracy and change. We observed that altering one mass in the system changed the theoretical acceleration as predicted by Newton's second law. While our experimental acceleration did not perfectly match the theoretical value, percent error allowed us to quantify the accuracy of our measurements. Comparing old and new acceleration using percent differences helped us evaluate whether our modification produced a significant change in the system. The use of the percentages rather than the raw numerical differences allowed for more meaningful comparisons. Overall, this lab strengthened our understanding of acceleration, theoretical modeling, and the importance of the percent error and percent differences in analyzing experimental results.